Look at this second problem here from calculating out probabilities of sample proportions. Here on number 2 it says, the superintendent of a large school district wants to know what proportion of middle school students in her district are planning to attend a four-year college or university. Suppose that 80% of all middle school students in her district are planning to attend this college. Or, sorry, 4 years college or university. What's the probability that a simple random sample of size 125 students will give a result within 7 percentage points of the true value? Wow. So, when I look at a problem like this, I go back to that 4-step process where I do the state, the plan, the do, and the conclude. So I'm going to start with my state. So I'm just trying to answer that last part. So it says, what's the probability that a simple random sample of 125 students gives a result within 7 percentage points? I'm going to change that within 7 percentage points to actual exact answers. If I'm going to be within 7 percentage points of 80%, what numbers am I going to be between? Okay. So if 80% is the middle, if I want to be within 7 percentage points, what would be the lower bound? What would be the higher bound? Or the upper bound?
74.
3% to 80. Okay, so I'm adding 7% and subtracting 7% from 80. So I want to be between those two values. Okay, so basically, what do I want to find here is what is the probability that a simple random sample of size 125 will give a result between 73% and 87%. So it might even help me to think about it like this way. What's the probability that my sample proportion, p hat, is between 0.73 and 0.87? And remember, p hat is sample proportion. So now I got to put together a plan. In order to find this probability, what would it be great to know about the distribution? Is it normal? Okay, so that's going to be my first question. Is the distribution approximately normal? Okay. Well, if you can remember, how do I check to see if a proportion or a distribution of a sample proportion can be considered normal? What two things must I show? If something has to be less than or equal to 10.
Population.
Well, not the population, but that's going to come up with the standard deviation. So remember that one. Well, let's look back in your notes.
Standard deviation.
Well, not a standard. Standard deviation deals with that population piece. So we're trying to show that it's normal. What does your note say? N times P, which represents the number of successes, and what's the other one? Okay, N times 1 minus P. As long as both of those are greater than or equal to 10, then it's approximately normal. Okay? So, our sample size here was 125. Our p-value, we expected 80% of them to say yes. So 80% of 125, I believe, is how much? I actually don't know that right off the top of my head. Let's see, minus 20, is it 100? Check my math. Okay. So then 125 times 20%, is that greater than or equal to 10? Yeah. So we can say our sampling distribution is approximately normal. So since it's approximately normal, then we can calculate out the mean. The mean of the sample proportion simply equals the population proportion. So it equals 0.80. Our standard deviation of our sample proportion equals the square root of p times 1 minus p divided by n. So in our case, we would be going 0.8 times 0.2 divided by 125. So I'm going to actually warm up my calculator here as we continue to give you a little time to write. So just got to load up my calculator here. It doesn't take too long. 5, 4, 3, 2, 1. Yeah.
On the plan, you have 100 is less than or equal to 10.
Oh, do I have to sign the wrong way? Oh, this should be greater than. Thank you. My goodness. Let's see how big of an eraser that is. I don't want that big. This should be, needs to be greater than it. I must have been saying less than. Come on, let's get back to the pen. So that has to be greater than or equal to, greater than or equal to. There we go. Alright, so now that we got our calculator here, large screen. Whoa, hate it when it does that. Jumped on me. So, clear this out. 0.8 times 0.2, 0.16 divided by 125. We want to take the square root of this answer to get our standard deviation. So our standard deviation about 0.036. Okay. Now, we have our mean, we have our standard deviation. Now, with our standard deviation, we should check, is our population greater than or equal to 10 times our sample? So So the question becomes, is our population greater than or equal to 10 times 125? 10 times 125 is 1,000 or 1,250. Is it safe to say that there's 1,250 middle school students in this large school district? Do you consider Hopkins fairly large? Okay. Okay, so if we're talking middle school, say if we say junior high, 7th, 8th, and 9th graders, are there more than 1,250 of them? Sure. Okay, so it is safe to assume there are at least 1,250 middle school students in this district. So now I actually want to calculate out my probability. So we get to the do part. So the do, I'm actually going to calculate out what's the probability that my sample proportion is between 0.73 and 0.87. So if I'm thinking about this, looking at my normal curve, here my mean is at 0.8. I'm going all the way out here to 0.73 and all the way out here to 0.87. I'm trying to calculate out that area right there. So it all comes back to these fun normal curves. They never go away. So z-score. So I have two of them. I got to do a lower bound and an upper bound. So my score 0.73 minus 0.80, my mean, divided by my standard deviation 0.036. So 0.73 minus 0.8, some of you probably already know that's negative 0.07 divided by 0.036. So negative 1.94. So now when I do the top one, 0.87 minus 0.80 divided by 0.36. Guess what that z-score is? Positive 1.94. Yep, because this is nice and symmetric. So this is like saying, what's the probability that, got ahead of myself, your z-score is between negative 1.94 and 1.94 standard deviations. So I can just calculate that out. Normal CDF, negative 1.94 to 1.94, and we got it. So second vars, normal CDF, negative 1.94 to 1.94, and we have our probability 0.9476. So now I can just write a quick conclusion statement. The probability that our sample will be between 0.73 and 0.87 is 0.9476. So to be within 7 percentage points, the likelihood that that will occur is almost 95%. Yes?
Will you just scroll up?
Sure. I can go to there if that's okay.
No, I just want to see like how much you could scroll. Cause I was half paying attention because I didn't know what's going on, but I was gonna see. You want to go for one call?
Well, what if you're on Wednesday, I know I almost said on Friday, but on Wednesday, we'd like break this into like 4 parts. We would be like, okay, what do you want to find? What's your mean and standard deviation? Can you use the normal approximation? Check your conditions for your standard deviation. Calculate it out, you know. So this basically doesn't break it down into those chunks.
Okay.
So this is like doing everything that you'd have to do for the problem. Alright. So that ends the notes actually technically for 7.3. So if you want to flip the page, we'll continue on with the 7.4, 7.5, and sample means.
Are you recording right now?
Yes.
So on your 2 pages, will this be under 7.4?
This will be under 7.4, yes. Okay. So, well, I just put it under 7.4 since it was a continuation.
Yeah.
So, in 7.4, 7.5, we're going to concentrate on calculating out basically probabilities that deal with sample means. Everything that we were doing in 7.3 dealt with a sample proportion because we are basically dealing with categorical data. Anytime you deal with categorical data, it's like yes, no, you're taking a look at percentage of people that would or wouldn't. You're calculating out a sample proportion. But when we deal with quantitative data, we're going to work with a sample mean. So a lot of times what you'll be wanting to do is you'll want to calculate out, for instance, you might be a company that, you know, produces batteries and they're going to take a look at maybe a sample of batteries and how long they last on average. So you'll want to take a look at the sampling distribution of your sample means, which is the symbol, excuse me, X bar. So knowing the right symbol notation is very important here. So first of all, when we talk about a mean and standard deviation of a sampling distribution X bar, how we go about calculating those. The formulas are actually a lot easier. Just like in a sample proportion, the mean of a sample mean, so this symbol mean of X bar is read like saying mean of a sample mean, is found by just taking the mean of the population. To find the standard deviation, so the standard deviation of X bar is like saying the standard deviation of a sample mean is found by taking the standard deviation of the population and dividing it by the square root of the sample size. And as we saw earlier in Chapter 7, as you increase your sample size, your variability, your standard deviation, decreases. How it decreases is by a factor of the square root of n. Okay. Now again, with your standard deviation, you want to make sure that your population is greater than or equal to 10 times your sample size. So what's nice is these formulas, just like when dealing with sample proportions, your sample means in repeated samples will behave similar to that as they do in sample proportions. So, however, to show, well, actually this is going to come up a little bit later, meaning, we know that to find the sample mean, the unbiased estimator is the population mean, which is just noted right up there. And we just already noted about how it's impacted by the square root of n for your standard deviation. So let's take a look at this first example right here. Oops, all right. So it says, suppose that the number of movies viewed in the last year by high school students has an average of 19.3 with a standard deviation of 15.8. Wow. Suppose we take a simple random sample of 100 high school students and calculate out the mean number of movies viewed by the member of that sample. So in question A it says, what is the mean of our sampling distribution x bar? So we're just simply wanting to know what's the mean of x bar. What should it equal? According to our formula, it should equal what? Okay, 19.3, which is the mean of the population. Okay. So now, to find the standard deviation of the sample, or it asks you in B, says, what is the standard deviation of the sampling distribution of x bar? So according to our formula, our sampling distribution will equal the standard deviation of the population divided by the square root of n. So our standard deviation was 15.8. Our sample size was 100 students. So our standard deviation would be 1.58 movies. So what it's saying here is, if I took repeated samples of 100 students, the mean of my sampling distribution would have a mean of 19.3 movies, and it would vary on average by 1.58 movies. Now this is great that we have a mean and a standard deviation, but when are means and standard deviations most useful? What is helpful to know about the distribution of the sampling distribution? What would be helpful, or when do we use them? What has to be true about the distribution? Like when we go back a page and we look at this problem, okay? What did we have to show before we could start calculating out the probabilities? Okay, what's the first sentence I said there in the plan?
Whether it's
Is it normal or not? Okay, so the question becomes, how do we show that in a sampling mean? Because it's not the same as a proportion. Okay, so there's two things that you have to worry about. First of all, if your population, what we'll look at is if you're dealing with a normal population versus a population that's not normal. Okay? If the population is normal, it's really nice. Okay? Because what happens is this. If our population comes from a normal distribution, any sampling distribution you do will also be approximately normal. Okay? So again, if your population is normal, then your sampling distribution is normal. Seems to make sense. If you sample from something that's already normal, then that sampling distribution should be normal. However, what happens if it's not normal?
This is sampling distribution.
Not quite.
You have to go through the steps.
Well, you don't have to go through all the steps. There's kind of a wish I almost had a applet for you, and if I get a chance after, I'll try to show you why this works. What happens is, what if the distribution is not normal? Okay. So we have something that's skewed to the left or skewed to the right. Stand up, sit down, fight, fight, fight. Okay? What happens is we have this theorem called the central limit theorem. And what happens is if you start taking samples of say size 1, then size 2, and size 3, and size 10, and start to take a look at those distributions, what will happen is however skewed it is, if it's majorly skewed to the right, as you increase your sample size, your distribution becomes less and less skewed to the point where it becomes approximately normal. Okay? The general rule, okay, is that if n is greater than or equal to 30, meaning your sample size. So if you start taking samples that are greater than or equal to 30, then your sampling distribution is considered normal, and we say this according to the central limit theorem. Okay. So basically, when we deal with sampling distributions and we check for normal conditions, we just have to state one of two things. Okay? First is, hey, if the population is normal, so is your sampling distribution. If it's not normal, this is the second one, then we say the central limit theorem, and you can use the abbreviation CLT to represent central limit theorem. Tells us that our sampling distribution will be approximately normal, in most cases n greater than or equal to 30. For our class, we just say, hey, if it's greater than 30, we're good to go. All right, let's take you through one more example, and then we'll call a day on the notes. Then if I get a chance, I'll try to pull up and just kind of show you with a simulation why this works the way it does.
So I'll have all the problems tomorrow.
Yep, we'll just finish up our notes tomorrow. Okay. So, number 1 says, the length of human pregnancies from conception to birth varies according to a distribution that's approximately normal, with a mean of 266 days and a standard deviation of 16 days. So in question A here it says, find the probability that a randomly chosen pregnant woman has a pregnancy that lasts for more than 270 days. Show our work. Okay? So, is this normally distributed? Is the population? What does it say right there? Approximately normal. So I can calculate out, well, what's the probability that X is greater than 270 days? Hi. Yeah.
Once I saw those calls, do you want me to just take those down?
No, because I haven't even collected the names yet. So we still have a few days away on that.
Thanks.
Yeah. So, anyway, so we're trying to find that a randomly chosen pregnant woman. So this is like saying n is equal to 1. So now, to do this, okay, if I'm thinking about my distribution, according to my information, my mean of x was 266. My standard deviation was 16. So I'm looking here, here's my mean at 266. I want to know what's the probability that the pregnancy will last 270 days or more. So this is like doing just a basic z-score problem. So z equals 270 minus 266 divided by 16. So that ends up being, I think, 0.25, because isn't it just 4 out of 16? So I'm looking at what's the probability that z is greater than 0.25. So I could go normal CDF, 0.25 to 999, so second vars, whoa, that's inverse tangent, second vars. Number 2, 0.25 to 999, so ends up being 0.4013. So the probability that a randomly chosen pregnant woman has a pregnancy lasting more than 270 days is 0.4013. All right. Question B says, suppose we choose a simple random sample of 6 pregnant women. So now instead of just choosing 1, we're going to let n equal 6. So we're going to let x bar equal the mean pregnancy length of the sample. What is the mean of our sampling distribution? Well, our mean of our sampling distribution should still just equal the mean of the population. So in our case, it should equal 266 days. So if I were to randomly select 6 women, the average of those 6 women's pregnancies should still have a mean of 266 days. Now, part C says compute the standard deviation of our sampling distribution of x bar. So, standard deviation of x bar should equal the standard deviation of the population over the square root of n. So, our standard deviation was 16 days. But now I'm taking a sample size of 6 and not just 1. So my standard deviation for this particular distribution should shrink considerably. So now, when I calculate this out, pull up my calculator real quick, 16 divided by the square root of 6, oops, I didn't need that little end parentheses, we get a new standard deviation of about 6.53 days. So it does check that our 10% condition is met. So, is our population greater than or equal to 10 times our sample? Well, our sample was only 6. So, is the population of pregnant women out there greater than or equal to 60? Yeah, pretty safe to say. It's safe to say there are at least 60 pregnant women in the population. I'm guessing there are some hospitals that get hit with 60 births just in one day. Have a busy day at that hospital. Probably more in a larger city, maybe like Chicago or New York. Alright, so now D says find the probability that the mean pregnancy length for the women in the sample exceeds 270 days. Okay, so now what we're trying to find is what's the probability. Let's try this again here. What's the probability that our sample will exceed 270 days? So my first question that I ask myself is the sampling distribution approximately normal? How do I know I can use the normal curve here? Okay, it told us that since the population distribution was normal, so will the sampling distribution. Be normal. So this one's nice. Because what if it was skewed? Could we do this one? No, because what's our n? It's only 6, and central limit theorem, it would have to be what? Greater than 30. So thank goodness on this one, our population distribution was approximately normal. So what we just saw in the previous 2 problems, our mean of our sampling distribution was 266. Our standard deviation from part C up here was 6.53 days. So now, I want to calculate out a z-score. The probability that z is greater than, so if I'm thinking about this visually, so I'm looking at here, 266, and I'm looking at 270 or more. So I'm still looking at this probability, but my standard deviation is much smaller. So, C equals my score 270 minus 266 divided by 6.53. This one here, 270 minus 266 is 4, divided by 6.53. Whoa, that's weird. Didn't take my division sign there. 4 divided by, there we go, 6.53. So we get a z-score of about 0.61. So to get this probability, we're going to go normal CDF from 0.61 to 999. So second vars, oh, did that again. Second vars, normal CDF, 0.61 to 999. So our probability is now 0.271. So notice how going from a sample size of just 1, it was over 40%. But if we take a sample size of 6, that probability drops down to 27%. Mainly because we're getting more accurate results. Our standard deviation is shrinking. So we could say the probability that our sample of 6 exceeds 270 days is 0.271. All right, we'll stop there for the note.